Okay, so hello everyone. My name is Tang. I'm an assistant professor at IPSA in Paris, France. Today, I would like to present our recent results on the fatigue life prediction using the crystal plasticity model as well as recent developed AI techniques. So, upper. 看不下来了。Okay. Okay, so I begin from the motivations. We know that the inclusion size will play a very important role on the prediction of the fatigue lifetime. It is already a long-term studies on that. For example, we can see some smaller inclusions like 10 micrometer and even larger one at the surface, correct surface like 50 micrometers and so on. So in fact, the largest inclusion will play a key role on the fatigue lifetime. So when you see the histogram in the center, if we just take a very small control area, something like 0.3, something like that, you can see that the largest inclusion size is pretty small. But when you enlarge the control area like 60 millimeter square, you can see that the largest inclusion can be found with a larger one. So the question is raised, when we observe tens of the steels, we can expect always a larger inclusion. So how we can estimate the largest inclusion size? So in order to address this kind of problem, typically we can try to use some statistical way, such as this one. You can see that the right hand side is the typical histogram of the inclusions. And also we can use the CDF, which is used for collect the statistical information. And the idea is, in order to avoid the laborers proceeding to find the largest inclusion, we collect the statistical information in a smaller volume, and then we can make use of the statistical way to predict the largest inclusion in tens of steels. So this is the basic idea. And for some recent works, we also know that some other alloys, such as titanium, while the fatigue correct initiation is completely different. Well, this is not only due to the large inclusion or defects. This is also the fatigue initiation is also introduced by the multiple interacting microstructure attributes, such as the textures, grain shapes, grain size, variations, and so on. So this is an example. If we build up a crystal plasticity model with one SVE, so one SVE is a statistical volume element, including around 200 grains. After the cyclic loading, you can see this is, for example, the string field. There is some hot spots in the particles. This is the localization of the plastic strain and stress in the particles. And we can expect that there will be some fatigue crack initiation in the particles. So here we introduce a way to estimate the location of the fatigue crack initiation. It is fatigue indicator parameters, or so-called FIPS. So the FIPS is surrogate measurements of the driving force of fatigue crack initiation. So let's talk about quickly some FIP modelings. Well, we know that the fatigue crack initiation is introduced by different micromechanisms, such as the slip band in the grains, all the grain boundaries. So different micromechanism will lead to different fatigue crack initiation. So here I just take a very typical one, which is often used for the titanium. So this is the FIPS is a function of the delta gamma alpha. In other words, plastic shear strain on each slip system. as well as its corresponding normal stress. So this is indicate the plastic dissipated energy or power. So this is a typical way, and in fact, there are many different formulas for the fifths. So let's see also some models. You know that fifths should not be the local fifth value. We should also consider the non-local fifths like this. From one single grain, we just build up the slip band based on the grain orientation. So depending on the slip systems, we can build up the slip band. And also we will calculate the slip band average flip in order to predict the slip band fatigue crack initiation. So let's see some results. This is just a very typical building modeling for the titanium in 1R SVE, and you can see this is the typical parameters. And this is the normalized CDF in terms of the FIP values. So when we carry out 10 SVEs or 10 realizations, we account for 10 times 200 grains. So we have 2000 grains. And the highest slip band average FIP locates here. And then when we carry out even more simulations, the random microstructure will generate even higher largest FIP value. So for example, if you see 100 SVEs, in other words, it is 100 times 200 grains, so it is something like 20,000 grains, and the largest FIP value will be even larger. So the idea is rather clear. It is if we carry out a simulation with even a larger volume, we can always expect that there will be some larger FIP values. In other words, a larger structure will lead to a weaker fatigue resistance. So we will come back to the initial question. So how we can estimate the largest FIP in terms of the structural sample? So experimental numerical experiments show us that when we carry out only one SVE, you see that this is a very teeny volume. The distribution of the maximum value of the FIP is something like that. I take two different textures as examples. And when we talk about the so-called subvolume of a component of interest, it is typically much more larger. For example, you can see from this structure, while the volume should be something like 10 to the fifth power SVEs, or even larger. So you can see that the maximum value of the FIPS is redshifted. In other words, it will display a larger maximum value of the FIP. So we use the so-called statistical method. It's extreme value statistics to collect the statistical information of a rather smaller volume. Wow, sorry, it is hidden. Around 100 SVEs, we just collect statistical information from these simulations, and then we use statistical method to predict the maximum value of the FIPS, accounting for the number of the grains. So this is a mathematical way, and also Also, we use a recently developed technique to carry out some verification and validation. So this is the DSR technique, which is named as deep symbolic regression. So this is an RNN-driven model, which will predict, provide us a sequence of the inputs as well as operators like plus, minus, log, and so on. So this AI data-driven technique can give us directly one explicit equation. So you can see this box will show you how did we carry out the simulation and collect the data, and we just get the data in terms of the sample size or the number of the grains. And then DSR could offer us directly the equations of the M and the mu is the statistical information of the largest fifth in terms of the number of the grains accounted for in our simulation. So you can see that after some manually simplification, we can get this result. And in this box, this is the statistical way. And based on this statistical way, you can see that the M and the sigma, they display the same value, exactly the same compared to the AI technique. So in other words, these two different methods give us the same results. So this is pretty interesting. So the consistency give us two important information. You know that the mathematical way we introduce a lot of assumptions. And well, for the data-driven way, we didn't introduce anything. It is just a data-driven way. And we can see that they are consistent with each other. So we know that the mathematical assumption used by extreme value theories is validated. And also we know that AI technique like DSR, the equations can be explained and are justified by the mathematical and physical principles. So this is the prediction of the maximum value of the fifth. And then another work, we carry out some simulations using crystal plasticity models. So we collect the statistical information of fifths. We already talked that we use the way to predict the maximum value of the fifths in terms of the sample size. So you can see that it is right-shifted with a larger number of the grains accounted for. And then I use a typical way, the so-called Coffin-Mason relation to build up a link between the fatigue crack formation lifetime with the maximum value of the fifths. So in this way, we can directly predict the fatigue lifetime in terms of the number of the grains accounted for. So let's see first order comparison. This is the sample size effect on the fatigue crack lifetime. You can see this is the CDF, in other words, the distribution of the fatigue lifetime in terms of the volume accounted for. So this one corresponds to 10 SVEs, rather smaller volume. And when we get a larger volume, like 10 to the fifth power SVEs, you can see that the fatigue lifetime will left shifted. In other words, the fatigue lifetime will be smaller. And the right-hand side, this is experimental measurements. So this is experiments using some bars with the same radius but different length. And they carry out some fatigue life measurements. And you can see that with a longer size of the bar, the fatigue lifetime will also right shifted. So you can see that the form of the PDF is very similar. So we know that the sample size is correctly accounted for. For saving our time, I just conclude here. So we developed one statistical based upper scaling scheme. We just use a smaller volume and we can predict the fatigue lifetime in a much more larger volume. And also this statistical framework is validated by extensive simulations and also data-driven SVEs. And also we introduce correlation equations to link the fatigue crack formation lifetime with the maximum value of the fifths. And also in this way, the effect of the sample size is accounted for. And also we discuss a lot on the texture effect on the fatigue lifetime as well. That works also very good. So I have finished. Thank you very much for your attention. Thank you.